determining the heart rate. So to determine, there's three areas or questions on the lab report that ask you to determine P wave on an ECG strip that's already uploaded, and PR wave and QT wave on your own. So the way you do that, using the fact that 25 millimeters distance is translated to time, you would count the number of little squares, okay? So you can count a half or a 3/4 if you want to. Here the line is slightly to the left of that line. I just went ahead and counted 3. And then you do a simple ratio. So we know that 1 second equals 25 millimeters. So how many seconds or a fraction of a second would 3 millimeters be? Okay? And you can flip these or whatever. So 1 times 3, class multiply, and divide by 25. So essentially, the easy way, without setting all that ratio out, is if you want to measure how long the T wave took, you would count for this one, be 1, 2, 3, 4, 5 millimeters. Take 5 and divide by 25. So take whatever the length of the event in millimeters and divide by 25. Okay, and that will give you a fraction of a second. To determine how many milliseconds that is, you want to move that decimal point 3 zeros. So 0.12 seconds or 120 milliseconds. Okay? So that on your own or your lab partner's strip, the first one asks you to determine the PR, and the PR is actually measured to the PQ. All right, so this would be 1, 2, 3, 4, 5, 6. 6 divided by 25, okay? 0.24 seconds, or again, moving a decimal point to the right 3 times, 3 places, 240. And then the QT segment. So this is half, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10.5 divided by 25, all right? Now, for the problem with the lab report. I was going through it to figure out which of these measurements I wanted to illustrate to you. And I came up on a problem. It's a decimal problem. And it's easy enough to correct, but the issue is that most of you have probably already opened up the lab report, and if you've already opened it, my correction won't correct it, if that makes sense. It's the way Canvas is set up. So I want to give you a warning ahead of time about that. So here you're determining the P wave on this strip that's already here. So here's the P wave, all right, and P wave, P wave. So count from your computer how many little squares there are, divide by 25, okay? And then move your decimal point, because you'll get a 0.08 or a 0.6 or a 0.05 or 0.08, and you'll convert that. Here, let's move on to where the problem is. So these on your own, I had put on its heart rate. I don't want heart rate. Move it down here. The correct answer from your ECG strip. Obviously, I don't know what the correct specific answer is going to be for each of your ECG strips. So what I did was I put a range, all right, of timing. That would be correct. So when you put that in here, if it falls within the range, and I made it rather broad, of the average PQ segment. The problem was I asked for milliseconds, but the example I gave, which I changed, was 0.4 to 1.25, and then I gave the answer, but I asked for it in milliseconds, and I gave the answers in seconds. So you can do one of two things. Either one is acceptable. You can put it, so that 0.12 that I had, that was 120, or the 0.24 that was 240, you can go ahead and put yours in seconds, and that will match up and be accepted as correct, okay? Or you can translate it to milliseconds like I asked, and 0.12 would be 120, and I'm gonna go through each of them and double check. So the Canvas will mark you wrong if you put it in milliseconds, but I will go back and give you the credit. So you can do either seconds as a decimal point. So don't go like 0.2357, just go 2 spaces. But again, I will go through and double check, because I don't want you to miss a point just because of whether it was seconds or milliseconds. So either way, I will double check your answers. You give it as seconds, as a decimal point, or as milliseconds as a whole number, either way, okay? So those are the 2 things that you need, other than your heart rate, that you need to measure on and place an answer here. And as I said, I put a wide range of acceptable answers to put on there. And if you have a picture, still have the picture that you uploaded, you can use that, just kind of increase the size a little bit so you can count it if it's too tiny, to be able to do it from the picture that you uploaded, or if you have the actual strip, that should be fine. Okay. Alrighty. Any questions on that part? So this is the last few questions on the PhysioX lab. Okay. Lab report. So as you go through the PhysioX, again, you're not submitting anything to me from that. You don't need to print anything off as far as data sheets or answers to the questions. That will be within the online lab report that you're working on for Sunday night. Okay. All right. Then, are there any questions regarding the autorhythmic cells or contractile cells that you're not clear about? I wanted to do just a little bit of, not really review, but highlight some areas of confusion with the cardiac cycle and pressure changes, okay? It looks scary, and it's not. Well, that's relative, I suppose. It shouldn't be, maybe put it that way. So if we're looking at pressure changes in the atria, that doesn't change very much. When we do our blood pressure, we're gonna do venous pressure in the right atria by estimate. We're not gonna stick a probe in your right atrium and determine it, okay? But I was at the doctor's this morning. My blood pressure was 77/48. And she took it twice. I was like, well, on Tuesday, I had a different doctor's appointment, a physical, more migraine medicine, and it was 110/77, so I'm fine. She said, you don't feel faint? And I said, no. And so then she tried it again on the other arm, and 20 minutes later, I said, I'll make the doctor yell at me and we'll get mad and my blood pressure will come up. So it did. It came up to 101/70. So when we do our blood pressures, even weird numbers can come up. I should have felt faint, but I wasn't. So pressures are what open valves and closed valves. That's what this cardiac cycle component is supposed to help you realize. Remember, we don't use the papillary muscles. We don't use the chordae tendineae to open or close the atrioventricular valves to which they're attached. It's the pressure due to either ventricular contraction or backflow of blood. So when we look at that diagram, we have the atrial pressure, and it's right atrial pressure, typically, but it doesn't really matter. We have pressure gradually increasing. There's a little bit of an increase because the AV valves close, but blood is continuing to come into the heart, and then it drops, and then it starts to build up again. So the lowest, not the very lowest, but the one that stays low is always atrial pressure. Okay. While the atria are filling, would the ventricular pressure be below or above atrial pressure? The AV valves are open, and the ventricles are filling. We call it the period of ventricular filling. The heart is at rest. The ventricles are in diastole, they're not contracting. So is pressure higher in the atria or higher in the ventricles? Yes. Because otherwise it would not go through the ventricles. It was higher in the ventricles, and the AV valves are open, the blood would be returning to the ventricles. So we draw our ventricular pressure below the atrial pressure. Because that's what happens when the ventricles relax and blood is flowing into the ventricles. All right? Then the ventricles, because they're contracting, there's a slight rise with that, and then we see the AV valves close, right, as the ventricles start to contract. So ventricular pressure becomes greater than atrial pressure. And when ventricular pressure is greater than atrial pressure, the higher pressure pushes on the backside of the AV valves and pushes them closed. So as soon as ventricular pressure crosses atrial pressure and becomes higher, at that point, the AV valves close, okay? And they remain closed until they open. All right, the pressure that's always the highest is in the aorta, right? So it becomes at its highest point when blood is leaving during ventricular ejection, and from that point on, it starts to fall as blood moves farther and farther away from the heart, okay? So as the atrial ventricles are filling, the semilunar valves are closed, and aortic pressure starts to fall, okay? While it's falling, ventricular pressure here is rising, and it's just a very short period of time. Change the angle a little bit here. And remember, AV valves are closed, pressure is rising, semilunar valves are closed too, because it's that rising pressure that eventually is able to push against the blood already still in the aorta, and it pushes the semilunar valves open, and we have ventricular ejection, okay? With blood going into the aorta, aortic pressure is rising as well. It's not higher than ventricular, but its pressure is rising. And then we have the ventricles relaxing because we are in the T-wave part of our ECG. So the ventricles start to relax and pressure drops as well. And as pressure drops, blood backflows in the aorta, and its pressure ends up being higher than the ventricular pressure. All right, so at this point, when ventricular pressure is higher than aortic pressure, the semilunar valves open. Okay, so for this narrow period of time, we have what we call isovolumetric contraction. AV valves have closed, semilunar valves haven't yet opened, okay? So isovolume, because the blood is not going anywhere. There's no blood coming in because the AV valves have closed, and there's no blood leaving because the semilunar valves haven't opened. And then we have, because the ventricles are relaxing, pressure continues to drop. And aortic pressure continues to drop as well as blood moves away. So at this point, the semilunar valves open again. Semilunar valves close again. Okay. AV valves are still closed until the pressure drops below the atria. When the pressure of the ventricles finally drops below the atria, we have AV valves opening, and there's another flow of blood into the atria. So again, we have isovolumetric, because here the semilunar valves close and the AV valves haven't opened yet. So in that narrow portion of time, we still have isovolumetric, because again, both valves are closed, blood's not coming in and blood's not going out, but the ventricles are relaxing, so we call this isovolumetric relaxation. Okay? So this period of time is ventricular filling. Systole, if you will. Okay? And this period of time is when the heart is in diastole. Ventricles are relaxed. Sorry, I did it wrong. My bad. This is ventricular filling because the AV valves are open. And this is ventricular ejection. So now when we look at pressure relationships, with that in mind, and that image, remember the AV valves open because of pressure and the semilunar valves close because of pressure. So an atrial pressure is greater than ventricular pressure. What are the AV valves doing? Are they open or closed?
Open?
Open, because the atrial blood flow into the ventricles is pushing the AV valves open. So they have opened, they're open, or they just opened, okay? As you can see that occurs right, it's ongoing here. When ventricular pressure is higher, than atrial pressure, then that's what pushes the valves closed, okay? So the AV valves close or remain closed. All right, now for the semilunar valves, that's the relationship between the ventricles and the aorta, or pulmonary trunk, but we usually focus on the aorta. So when aortic pressure is greater than ventricular pressure, semilunar valves are closed or open? Closed. It would be that first half of the picture. So semilunar valves close or remain closed. And then when ventricular pressure becomes greater, then aortic pressure, that would occur right here. Okay, and the semilunar valves open. And remain open until this becomes the case again. So we're toggling back and forth between those situations. All right, so what happens when aortic pressure is higher than ventricular pressure? Sorry, the other way around. Atrial pressure is higher than aortic pressure. What's going on then? That never exists unless your dad or something else is happening. Look at the difference. Our highest aortic pressure, textbooks still say that average blood pressure is 120/80. Although now if you have a blood pressure more than 120, they say that's hypertensive, or at least pre-hypertensive. Used to be that was the average, and it wasn't until you were 130/80. So a lot of books will have this at 120. Atrial pressure is around 5 to 8, 5 to 10. Atrial pressure never gets that high. Aortic pressure never gets below that unless there's no pressure at all, because your heart isn't beating, okay? So you don't want to choose any relationship of pressures where atrial pressure is higher than aortic pressure, okay? So you'll usually see these answers in groups of 3 because we have 3 pressures. So at this time of ventricular filling, aortic pressure is greater than atrial pressure, and atrial pressure is greater than ventricular pressure. So we don't have any valves between the aorta and the atria. So what we look at is aortic pressure is greater than ventricular pressure, so semilunar valves are closed. Atrial pressure is greater than ventricular pressure, so AV valves are open, all right? So you would see that written as aortic pressure greater than atrial pressure, greater than ventricular pressure. And so to read that, you're going to say, okay, aortic is greater than ventricular, because there's no valve between the aorta and the atria. So aortic pressure is greater than ventricular pressure, therefore semilunar valves are closed because blood's flowing back into those little cuts, but closing them. And atrial pressure is greater than ventricular pressure, so AV valves are open. Okay? So this map kind of helps you figure that out. If we're talking about ventricular ejection, then we have ventricular pressure greater than aortic pressure, greater than atrial pressure. And that gives you the sequence of what you see here. So if ventricular pressure is greater than aortic pressure, semilunar valves are open. And if ventricular pressure is greater than atrial pressure, AV valves are closed. Okay? And then we have the conditions of the isovolumetric relaxation and contraction. All the valves are closed, and you can't tell by the valves being closed whether it's isovolumetric contraction or isovolumetric relaxation. You can't tell. Just all the valves are closed. All right, so when that happens, you can see that aortic pressure is higher, again, but ventricular pressure and atrial pressure are flipped. All right, so we have aortic pressure is higher than ventricular pressure. That closes the semilunar valves or keeps them closed. Ventricular pressure is higher than atrial pressure, and that keeps the AV valves closed. Okay? So it helps if you get confused to just look back at that graph and realize that unless the blood is leaving the ventricles and going into the aorta, the aortic pressure is always going to be the highest. Okay? It's only during ventricular filling, it's only during ventricular ejection that ventricular pressure becomes higher because it's able to push blood through the aorta. Okay? So you've probably noticed there are some worksheets to help you process through this and get used to the terms, and there's answers posted as well that you can double check after you're done working with the worksheets. Okay? Alrighty, I erased my list of things to do, but any questions on this? Okay, you can ask.